The alveolar gas equation tells us how much oxygen is in the alveoli. It's super important because the oxygen in the alveoli is what determines how much oxygen gets into our blood. Here we can see the equation, but for exams and for clinical practice, we have to understand the logic behind this formula. So let's break down this formula step by step. The first value is pressure of oxygen in the inspired air. Basically, it's the amount of oxygen in the air you breathe in. And as we see, the normal value is 150. So let's explain where do we get this number. So here we have 4 compartments. It's airways, alveoli, blood and tissues. In the atmosphere, we have a lot of gas molecules. The total amount of gas molecules give us barometric pressure. And in normal condition at sea level, barometric pressure is 760. From total amount of gas molecules, oxygen share is always 21%. This value is constant, so 1/5 of all gas molecules is oxygen. As we breathe in, air goes into the airways, and if we calculate, the amount of oxygen that incomes to airways with inhalation is 160. The gases that income to airways gets warmed to body temperature and humidified by our nose and airways. By humidification, we mean that air becomes saturated with water pressure. Basically, by humidification, we make from a dry air the more comfortable humidified air, which is more suitable for our airways and alveoli. But there is a price for comfort. As we add water vapor to the mix of gases, water vapor has its own pressure, which is 47. And because of this, water vapor takes up space. It pushes out some other gases, including some amount of oxygen. So we sacrifice some amount of oxygen just to make air more comfortable for our alveoli. And the actual amount of oxygen after humidification we call pressure of oxygen in inspired air. And as we calculate it, we get 150, which is the value that you saw in formula. Exactly this amount of oxygen in normal condition goes to the alveoli. So now we understand the first part of the formula. But what about the second part? Why do we include into the equation the partial pressure of carbon dioxide? So let's explain the role of carbon dioxide and respiratory quotient. During cellular respiration as a waste product, tissues produce carbon dioxide. After this, carbon dioxide diffuses into the blood. And the partial pressure of carbon dioxide in the arterial blood normally around 40. Because carbon dioxide diffuses easily between blood and alveoli, we assume that the amount of carbon dioxide that incomes to the alveoli is equal to 40. But the space inside the alveoli is limited, because simultaneously with carbon dioxide we also have income of oxygen. So how do we know how much space takes carbon dioxide? For this purpose, we have respiratory quotient, which equals 0.8. Basically, this value tells us that for every 1 unit of oxygen that incomes to alveoli, our body produces 0.8 units of carbon dioxide. So, knowing this, if we divide partial pressure of carbon dioxide in the blood on 0.8, we will have the actual amount of carbon dioxide in the alveoli. In this case, it's 50. So, if the total amount of oxygen that incomes to alveoli is 150, and 50 is already occupied by carbon dioxide, the space that can be taken by oxygen is just 100. So, in normal condition, the pressure of oxygen in the alveoli is 100. After the alveoli, oxygen diffuses into the blood, and at this moment, everything depends on alveolar arterial gradient. Basically, this gradient shows how easily oxygen can diffuse into the blood. And the major factor that in normal condition determines alveolar arterial gradient is age. The older the person, the more difficult for oxygen to diffuse into the blood. The normal values for alveolar arterial gradient is 5 to 15. So the actual amount of oxygen that incomes to the blood can be calculated as the amount of oxygen in the alveoli minus alveolar arterial gradient. In this case, let's assume that AA gradient is 10, so it gives us 90. So the partial pressure of oxygen in the blood in this case will be 90. And from the blood, oxygen is delivered to the tissues, and as we know, tissues use oxygen for cellular respiration. So it's the entire process of breathing. And for exams and for clinical practice, we have to know how different pathological states affect alveolar gas equation. The first clinical scenario is hypoventilation, which can occur in case of opioid overdose or during COPD exacerbation. In case of opioid overdose, the problem is decrease in respiratory rate. In case of COPD exacerbation, the problem is shallow breathing, which limits the time available for lung emptying. The feature that unites these two conditions is increase in partial pressure of carbon dioxide in the blood. Let's suppose that the pressure of carbon dioxide in the blood becomes 60. So the amount of carbon dioxide that incomes to alveoli becomes 60. Now, if we divide 60 on 0.8, we will get the actual amount of space occupied by carbon dioxide in the alveoli. And in this case, it will be 75. Because the total amount of space is 150, and 75 is occupied by carbon dioxide, the space that can be taken by oxygen is just 75. After the alveoli, oxygen diffuses into the blood. Let's assume that there is nothing wrong with alveolar arterial gradient, so the partial pressure of oxygen in the blood will be 65. And by the blood, oxygen is delivered to the tissues. And because now tissues will have 65 oxygen instead of normal 90, tissues will be in hypoxic state. The second scenario is high altitude. Let's assume that person is in the mountains. The problem with high altitude is low barometric pressure. Simply speaking, the higher you are, the less gases are present, including oxygen. So instead of 760, in high altitude we have 500 units of gases. As a result, the less amount of oxygen will income to the airways. So instead of 160, in this case we will have 105. And after humidification, the actual amount of oxygen decreases even more. So in this case, pressure of inspired oxygen will be 95 instead of 150. Because of this, we have a smaller room for oxygen. And because in alveoli we already have 50 units of carbon dioxide, the space that can be taken by oxygen is just 45. And even with normal alveolar arterial gradient, the partial pressure of oxygen in the blood will be 35. So our tissues will have only 35 units of oxygen instead of normal 90, which means that they will be in severe hypoxic state. The next scenario is VQ mismatch. The problem here is decrease in available surface area between alveoli and blood. For example, due to the emboli that disrupts perfusion, or foreign body obstruction that disrupts ventilation. The logic here is that with decrease in available surface area, the diffusion of oxygen into the blood decreases, which means that AA gradient will increase. Let's assume that AA gradient becomes 50. So the partial pressure of oxygen in the blood will be 50. And because tissues will receive not 90 but 50 units of oxygen, they will be in severe hypoxic state. And the last scenario is diffusion impairment, in case of pulmonary fibrosis, for example. If the alveolar membrane becomes thicker, this will decrease the diffusion of oxygen into the blood, which means that alveolar arterial gradient will increase. Let's assume that AA gradient becomes 20. So the partial pressure of oxygen in the blood will be 80. And because tissues will receive not 90 but 80 units of oxygen, they will be in mild hypoxic state. Hope you like the video, press like and hit subscribe button, and may the force be with you.